Good afternoon. My name is Rüdiger Scheider from University of Kassel, the Center for Environmental Systems Research. And today I'd like to give you a short overview of a modeling framework for assessing resource footprints of the German bioeconomy that we are currently developing in my research group. But let's start with a little bit of background and context. In its national bioeconomy strategy, the German government defines different guiding principles and goals of a sustainable bio-based economy. And this so-called bioeconomy is oriented towards nature-like material cycles, it supplies sufficient and healthy food, and it also delivers high-value products and energy from renewable raw materials. And all this is achieved while preserving natural resources. And from this starting point, we argue that it is important that the management and controlling of the societal and economic transition towards such a bioeconomy requires an appropriate monitoring. And for this, we need specific tools in order to analyze to what extent the aforementioned goals are fulfilled. Building on this is the SYMOBIO project. It's funded from the BMBF, and within this project, 8 institutional partners are aiming to develop the scientific basis for a systemic monitoring and modeling of the bioeconomy in Germany. The project started in 2017 and will run until 2021. A central objective of the project is to account for different dimensions of sustainability at both the national and the international level. Now in this talk, I'm going to present the concept and also a first application of a new modeling framework for the assessment of resource footprints as one important element of the systemic monitoring that we design as part of SYMOBIO. An important outcome of SYMOBIO is the pilot report for the monitoring of the German bioeconomy that was published earlier this year. And it brings together different sorts of analysis and introduces a potential structure of a bioeconomy monitoring. The whole report can be downloaded under the link that is shown on this slide. But let's start with the idea of footprints. So what are resource footprints? So here I try to delineate the concept. Here it's the use of biotic commodities for production, consumption, and infrastructures within a specific region imposes environmental pressures and impacts related to the production of this biomass, for example, in agricultural and forestry systems. And this either within the region where it is consumed or in regions that export this biomass to the region under investigation. This example that is shown here on the slide, we see information on so-called virtual water import from the European Union. So this means here we track the water which is embedded in raw materials, biotic raw materials, and products that are imported to the European Union. And we will see later how this water footprint is defined and how we can use this indicator. How are footprints integrated in SYMOBIO? Here we see this conceptualization again in a little different form. We see in the central aspect here is to track the environmental pressures from consumption, production, infrastructures where biogenic materials were used. These environmental pressures, or if we go one step beyond, also impacts, might be assessed with these footprints. And in SYMOBIO, we differentiate between 5 different footprints. It's the agricultural land footprint, the forest footprint, water footprint, climate, and material footprint. And the results from the assessment of these footprints then feeds directly into the monitoring system, as we see here, but can also be used as part of an evaluation where we compare the results to global reference values, for example, that are used for giving thresholds for sustainable resource use. This data is, or this information is highly debated at the moment, and I won't refer again to this evaluation part, and I will concentrate on the technical aspects, how we achieved to calculate these different resource footprints. What are the objectives of our study? So first, let's have a look at limitations of available footprint analysis. So there are many studies available, but only few of these consider multiple footprints in a consistent manner, which from my perspective would be necessary to identify overlaps and trade-offs between them. Then only few of them analyze temporal developments of footprints, which would be an essential element for continuous monitoring. And only few of them include a spatially explicit and process-oriented representation of environmental aspects. With our modeling framework, we now try to overcome these limitations by first implementing a conceptual approach that supports the integration of different data sources and models. And second, by the integration of global, economic, and spatially explicit models for a more detailed representation of processes within social environmental systems. Third, by supporting the assessment of multiple footprints with consistent input data and modeling approaches. And fourth, by supporting the analysis of historic and future developments. The latter, for example, in form of trend and scenario analysis. The next slide gives an overview of our modeling framework. It's a classic 3-tier approach. Tier 1 is a data tier. Here we have different databases collecting statistical data about agriculture and forestry, international trade, more elaborated data, so example, multiple region input, output tables, and very different sorts of environmental data, ranging from climate data to soil data to land cover data. Then we have Tier 2 that integrates different global simulation models. We can differentiate between economic models, so for example, material flow models, CGEs, and on the other hand, spatial models that are related to land use change analysis and also very important for the examples that I will show you later related to hydrological processes. Then on the third tier, we find the algorithms to calculate the actual footprints based on the data that is provided in our system and the results from the different simulation models. So now let's look how a typical study with this framework is set up. As an example, we've chosen a simplified version of the water footprint. So first, some basics about a water footprint. So this water footprint is an indicator to measure the appropriation of water resources by human activities. It was first developed by Hoekstra and Mekkonen in 2011. The objective is the calculation of the water footprint by cultivation of crops that are exported to Germany either as raw product or in processed form in 2000 and 2050. This means we have this component of temporal change also in it. In the original publication, the water footprint includes 3 elements. The use of precipitation, that's a green water footprint. Then the use of ground and surface water for irrigation, that's a blue water footprint. And the amount of water that is necessary to achieve a degree of dilution to reduce the concentrations of harmful substances under specified thresholds. That's a gray water footprint. Here in this study, we concentrate only on the blue water footprint. Plus, we do some additional analysis regarding the location of these footprints in water-stressed regions. So here it is shown which elements of our modeling framework are used to calculate this water footprint. So first of all, we start with a multi-regional input-output table to derive a material flow model that depicts the flows of biomaterials from exporting regions to Germany, and also gives information on the production of biomaterials within Germany. Then, in the second step, we couple this information with a global land use model, which is again coupled to a global hydrological model. The results from our modeling analysis is then used to calculate the footprints, the water footprint in this specific case. And of course, both spatial models use the same database regarding environmental data. So, for example, they use the same type of soil data, they use the same type of climate data as input, and so on. Here we see a concrete implementation of the framework. The data component is given by ExioBase, a multi-region input-output database. We use this to derive material flow models for biomass production at country level, and a material flow model for export quantities of biomass to Germany. Then in the second step, we use the global land use model Landshift to create a spatial allocation of irrigated cropland. Based on this allocation, which is generated on a 5 arc-minute global grid, we use the water gap hydrology model to calculate irrigation water use on one hand and water stress on catchment level. And then we bring together, we combine this information on irrigated water volume and water stress with the material flow data in order to generate the water footprint per water stress category. Let's look a bit deeper in the details. We use the global land use model Landshift to generate a global cropland pattern with a spatial resolution of 5 arc-minutes. We further differentiate between 8 different crop types and crops that are cultivated in a rain-fed system and in irrigated systems. Here we see as an example the distribution of irrigated cropland with cotton in Central Asia. Then in the second step, water withdrawals for each raster cell where a specific crop is grown are calculated. In the first step, here we calculate irrigation water requirements using the crop water model approach, which is implemented within WaterGap 3. This irrigation water requirements are crop-specific evapotranspiration minus effective precipitation. Then water withdrawals are irrigated water requirements multiplied with irrigation efficiency. The whole principle of the model is shown on this slide below the map. Water stress calculations are also done with water gap 3. Water stress is calculated on basin level, and as an indicator for water stress we use the WTA, the withdrawals to availability ratio. This means we divide water withdrawals by industries, households and irrigation by water availability. And this is basically the runoff that is calculated from the hydrological part of the water gap model. Water use of industry and households are taken from other studies where water gap 3 was used. The irrigation component is calculated by our modeling framework. We differentiate between 3 water stress classes. High water stress delineates a WTA larger than 0.4. Medium is between 0.2 and 0.4, and low water stress is in catchments with the WTA smaller or equal 0.2. Yeah. Why is looking at water stress important? Here we see the results from a recent study that shows that water withdrawals from households and industry will most likely increase dramatically until 2050. And so this means there is a strong likelihood that there will be growing competition for water resources between these two sectors and the agricultural sector where water is used for irrigation purposes. So the results of our study portrays water withdrawals related to biomass exports from different regions to Germany. And we can visualize these results in different forms now. For example, as shown here in the A section in form of global maps. So here we see the amount of water withdrawals in different world regions given in million cubic meters. And below there's another form of visualization here. We see differentiated for different crop types the total water withdrawals associated with the imports of these crops that are consumed or used for production infrastructure in Germany. And this information is further subdivided in the water stress classes of the exporting regions where these crops are basically cultivated. And what we see here, for example, for cotton is that in 2000 a large share is produced, the largest share is produced in low water stressed regions, but also a significant share is produced in high water stressed regions. So summary and outlook. We introduced the concept of a modeling framework for the assessment of resource footprints as a component of the German bioeconomy monitoring. As an example, we showed the application for water footprint calculations using a combination of different spatially explicit process-oriented simulation models. In our case, it was the global land use model Landshift and the global hydrology model Water Gap 3. Use of dynamic models allows us now the analysis of historical periods, as I've shown you in this presentation, but also for future scenarios with changing boundary conditions. So, for example, we can take into account climate change effects on evapotranspiration or effects of socioeconomic developments on the expansion of agricultural area and on further increases of land competition, for example. Then examples for the assessment of multiple footprints and for the analysis of future trends are outlined in the pilot report on bioeconomy monitoring in Germany. I've already pointed out that we use land shift not only to calculate the spatial distribution of irrigated cropland, but also on rain-fed cropland. So this means we can use the same sort of data also to generate information, for example, for the agricultural footprint, which then is of course consistent with the underlying assumption for the water footprint. So what are we aiming at the future? So further development of the framework will be done by incorporating land use related impacts on greenhouse gas emissions and on biodiversity losses. And this work will be conducted in the next 9 months. It means in the second part of the SYMOBIO project. With that, I thank you very much for your attention.